the third talk in this session, which will be given by Douglas. So Douglas, I give the word to you.
Okay, can you hear me?
I can hear you, yes.
Okay, thank you, Tony. I will start to share my screen. Okay. Okay. Hello to everyone. My name is Douglas. I'm an industrial engineering PhD student from São Paulo State University in Brazil. And now I will present the work two-dimensional cutting stock problem with usable leftovers, an exact and non-exact approach. This work is related to my PhD project that I've been developing along my supervisor, Professor Adriana Cherri, also from Unesp, and my co-supervisor, Professor José Fernando Oliveira from University of Porto. In this presentation, I will start with a brief problem definition. Then I'm going to describe the proposed mathematical model and heuristic procedure used to solve the problem. Then I'm going to show the results of some computation tests and finally give some final comments. Well, the two-dimensional cutting stock problem with usable leftovers consists in cutting plates, two-dimensional plates available in stock in order to produce a set of smaller demanded items. In this example, to attend the demand, we have to use both plates available in stock, and this is a possible solution that gives us 27% of waste, okay, very high waste. However, if we allow the generation of a usable leftover, we can decrease this waste to 5%. So it's a very simple example, but that shows the main advantage of allowing the generation of leftovers in this two-dimensional cutting problem. So the strategy of the mathematical model that we are proposing is at the same time create cutting patterns and determine their frequencies. So the cutting patterns are built using the concept of strips. So each plate is divided into horizontal strip, and each strip has the height of each strip is equal to the height of one of the demanded items. And after a strip is initialized, another items can be allocated side by side in each strip. Moreover, we use a strategy that we call macro items, in which each macro item is composed of two or more items allocated one above another. And the upper bound for the height of a macro item is the height of the largest demanded item. So in this example, the largest item is item 1 with height 20. So there are 5 possible combinations of the demanded items that give us 5 macro items. And these macro items, just like another item, regular item, can initialize a strip and be allocated side by side on each strip. So in this context, we have the parameter HF that indicates the set of possible heights for strips. That is the different heights of items and macro items, and the binary variable Y indicates which height is assigned to each strip of a cutting pattern. So the usable leftovers, we allow a cutting pattern to generate just one leftover, okay, from a standard plate. Standard plates are plates that we buy from providers from other companies, okay? So in our stock, we can have standard plates or leftovers from previous cutting process. A leftover never is generated from another leftover, okay? So just standard plates can generate leftovers. So the height of a usable leftover must be this is the variable LO that indicates the height of a leftover in the pattern J for a plate S. This height must be in the interval indicate here, in which H are minimum and maximum are values between 0 and 1, and HR maximum must be greater than HR minimum. So the height of a leftover of the leftovers depends on the height of the cut plate. So in our objective function, we minimize the total area of cut plates, okay, minus the area of generated usable leftovers. And here we use a parameter alpha that we call reuse rate that is used to give us a more realistic scenario, since we cannot guarantee that usable leftover that we generate today will not give us waste when it will be cut in the future. So we use this reuse rate in our objective function. So the constraints, we have a set of constraints that guarantees that the size of the plates is not exceed by height. Okay, so the height of strips and the leftovers cannot be higher than the height of the plate. Okay, the height, we need two different constraints, okay, for standard plates that can generate a leftover, and a leftover that cannot generate another leftover. We have the constraint of width, the plate width, the constraint of the strip height. Okay, so after a strip is initialized, we cannot allocate an item higher, item with height greater than the height of the item that initialized the strip. One constraint for items and another for macro items. We have the demand constraint, stock constraint, and this constraint limits the maximum number of generated leftovers. So this is a very important parameter, capital U, that indicates the maximum number of leftovers that can be generated for each problem. So the heuristic procedure that we are proposing, it has two steps. In the first step, we create a set of initial cutting patterns. Okay, we try to find the best cutting patterns in terms of waste for all types of plates in stock. Okay, with and without usable leftovers. After this set C of initial cutting pattern is created, the procedure goes to step 2, in which an adaptation of our proposed model is solved using the cutting patterns created in step 1. So the model here in the step 2 of the heuristic procedure will create will create just one new cutting pattern for each at each iteration. Okay, but it can use the initial cutting patterns created in step 1. So here we have this figure that explain this procedure. So the procedure starts here, creating a set of initial cutting patterns. This V pedometer indicates the type of plate for which the adapted model will create a new cutting pattern. Okay, so the adapted model is solved using C. It can build one new cutting pattern for V, for plate V. If a better solution is found, then this new cutting pattern created is added to C, so C is updated, and it goes back here, this step, and the adapted model is solved again with the new configuration of C. If here a better solution is not found, so the procedure updates V. Oh, I'm sorry. Here, the procedure checks if V is equal S plus R. S is the number of types of standard objects, standard plates, and R is the number of types of leftovers in stock. So if V is equal S plus R, so it means that the procedure already tried to create a new cutting pattern for all types of plates in stock and could not improve the solution. So end of procedure. If V is not equal to the number of plates in stock, so we increment V and then goes to this step again and start over. Okay, this is the idea of the heuristic procedure. So for the computational tests, we first we used instances from the literature, 20 instances from Andrade et al. 2016. In this paper, the authors proposed two mathematical models to solve the two-staged two-dimensional cut-stock problem with usable leftovers. And these two models, the only difference between them is that in model 1, M1, items demand is equals to 1, just like in the bean packing problem. In model 2, items of the same time are grouped together. The objective function of the model proposed by Andrade is minimize the total area of the cut plates, and among this minimum value of area, choose the one that maximizes the area of usable leftovers. So it's different from the objective function of our model. So for this set of tests, we use this objective function. Okay, so we are in the same space of solutions of Andrade, of the models from Andrade. And all these models were coded in OPL and solved using Cplex version 1210. Oh, sorry. Here. So these are the results for the two-stage models. What that means? What does that mean? The models proposed by Andrade are two-staged. So our models here in those tests could not use the macro items. So because macro items turns our problem a three-staged problem. So For the two-staged, for the 20 instances, here highlighted in bold are the smallest, the shortest times for each instances. All the models found the same solution, the same optimal solution. Okay, just the time varied between the models, the two models from Andrade and our model, with capital U equals 1 and capital U equals 5. And here, with the green arrows, are the instances where our model could found the optimal solution in a really short time compared with the models from Andrade. For the three-staged models, that means with macro items, here we have a new column that indicates the number of macro items for each instances. We have these three instances that are very interesting because they have a, a real large number of macro items with impacts in in the the models, okay, in the solving time. So for these instances, the model from Andrade and our model could not find an integer solution in the time limit that was the time limit was 1 hour. And here, with the green arrows again, are the instances where our model had the best performance in terms of time. The solutions are the same, the optimal solutions. We also ran tests with randomly generated instances. Okay, these are the 16 classes we tested, varying the item size, the number of types of items, and we tested 10 instances for each class. Here we describe each class of instances. This last three columns indicates the average number of plates in stock, okay, going from 7 to 27, the average number of demanded items, and the average number of macro items. We ran these tests varying capital U from 0 and 5, the reuse rate 90%, and the interval for the height of leftovers, we use HR minimum and maximum 40 and 60%. So for this test with instances randomly generated, we compared with the model proposed by Furini. And this model, the strategy of this model is cut plates in stock through horizontal and vertical guillotine cuts, and the resulting plates of these cuts can also be cut again, or they can be kept to satisfy the demand if their size is equals to the size of one of the demanded items. These are the results, okay, comparing the model from Furini, our model, and the heuristic procedure. And highlighted here in green are the instances where our model was better in terms of time, was faster, okay, but found the same solution than Furini. However, in all the other classes, Furini was the model from Furini has found better solutions than our model. Here, these highlighted instances had 3 and 5 types of items. So that means these were the smallest, the small instances that we tested. Here in red is a case in where our model here. I'm sorry, I will pass to the next slide. Here, in comparison, the model with our heuristic procedure, these were the instances where the heuristic procedure was better than the proposed model. Why is that happened? Because these classes, for these classes, we have more types of items, so they are larger instances. So the heuristic was able to find better solutions. Okay, and the same, okay, for tests with u equals capital U equals 5. Here, those tables equal u was equals 0 because Furini does not allow the generation of leftovers. Here on the green arrows indicates where our model was best and where the heuristic was best. Okay, so my final comments, as we can see in the results, the model had better results for classes with few types of items, and the heuristic was superior and had results closer to Furini for the classes with more types of items. And we have an ongoing research that we are testing the possibility of considering uncertainty in the demand for items. I would like to thank FAPESP that support this research. Thank you.
Okay, Douglas, thank you for the nice presentation. So questions? Okay, Jeroen?
Yes, thank you, Douglas, for your presentation. If I understand it correctly, the value of a leftover scales linearly to its height, right? So if solution A contains, let's say, 2 leftovers, which with each height of 100 centimeters, it would be superior to another solution with only 1 leftover that has a height of, let's say, 180 centimeters. However, I think in the real world, it is sometimes solution B or the second solution would be preferred over the first solution. Is it possible to adapt your model to that change in objective, or would it require a completely different approach? Thank you.
Okay, I think that what you suggest is easily adapted for our model, and we consider other strategies for our objective function, and I think we can use this type of solution that you suggest. We will talk about this, and we can adapt, yes, easily. I think I don't see a problem.
Okay, thank you.
Okay, other questions? Yeah, Julia?
Thank you. I wasn't clear, and apologies if you covered this, whether you need to incentivize the use or reuse of the leftovers. I can see a situation, and I've done some work on this myself, where you just create more and more and more leftovers, which you have to hold in inventory.
I'm sorry, Julia. I did. Can you repeat, please? I'm sorry.
So whether when you are planning your solution and you have leftovers available, do you need to incentivize the use of leftovers over the use of new, fresh stock sheets to avoid the case where over time you create more and more leftovers that you have to then hold in stock?
At this moment, we can try to control this by changing the capital U parameter. So if we have like a large amount of leftovers, a large number of leftovers in stock, we can like set the capital U like 0 or just 1 to avoid that more leftovers be created. At this moment, that what we can do. Just like the model is today, but we can add another parameter, just like the reuse rate, that penalize or the generation of a leftover, or I think this is an option.
Mm-hmm.
Okay.
Thank you. So just to follow up comment, we did some work on a similar problem with usable leftovers, and what we tried to do is take account of the cost of storing leftovers versus to trade off against the cost of using them, because you may find you get a worse packing solution if you force the use of leftovers. Mm-hmm. But of course you're then incurring some kind of storage cost the more you produce and store them. So that was how we tried to sort of control it. Unfortunately we never published the work, but we do have the thesis if it's of interest.
Okay. Thank you.
José, you have a follow-up on that?
No, this is a very interesting discussion. Actually, we have another paper, but on the one-dimensional problem with leftovers, in which we go that extra mile, and so work with this is a work with Adriana Cherri, and what we are doing basically is looking at a problem in the real context of a multi-period problem. And what happens is that each time we generate a leftover, we don't consider that 100% of the leftover is usable in the future. So we penalize by immediately imposing a waste on that leftover. It pays immediately a certain amount of waste. So generating a leftover is not actually not having any waste. It already pays, let's say, some waste. But then, when we are in the following period, when we go to the stock and take the leftover out, it costs less because it has already paid in the past part of the waste. So by this mechanism, we somehow control the generation of leftovers. It has to be better than the average waste, I would say, generating a leftover, and then we there is an incentive afterwards to use it. On the top of that, we have to consider that from a logistics point of view, generating a leftover requires some operations in the warehouse. And so there is a fixed cost for generating the leftover also. So altogether, I think that we have that better treated in the one-dimensional problem, where it is easier because it's one dimension. And now what Douglas is doing is extending the problem for a two-dimensional setting. And I think that we will incorporate this strategy to incentivize the use and not allow the explosion on the number of leftovers. Being that, for the moment being, we just consider that we have a finite number of leftovers that can be kept in a given moment in stock. So if you have 4, you can generate 1 more, 5, and if you spend 5, you have room to generate more. But it's a very naive way of doing it, of course. But very interesting question.
Okay, so maybe final call for a last question, or no? Okay, so then we can close this session. Actually, we consumed almost all the time we had, so I think there's a break now for 15 minutes, and then see you in the next session. And thanks the speaker again, of course.